So we're going to talk now about a running example we'll carry through the bulk of our discussions about Project Reactor, giving us a chance to showcase its many operators that work with monos and fluxes. And so we'll also get a chance to see parallel fluxes at some point along the way as well. So the basis of this series of examples is a class called the BigFraction class. I've used these in my other courses, so if you've been in my other courses, I apologize for this quick recap, but it's a fun little abstraction that you can do all kinds of things with. So what is a big fraction? It's an arbitrary precision fraction that uses so-called big integers for the numerator and denominator of the big fraction. So if you are familiar with big integers, they can be infinite precision. You can have integers that go on forever. Well, not forever, but very large. We then use various factory methods provided by BigFraction to reduce fractions. If you remember, like your 5th grade class where you were learning about fractions, you know that if you take 44 55ths, you can reduce it to 4/5, and so on. There's also other factory methods that will create non-reduced fractions, and I'll explain why you would do that in a second, and then later reduce them. So you might start out with 12/24, and then later, ... convert that into 1/2. Why would you do that? Because it takes a while to reduce large, big fractions, and so we might choose to do those concurrently in other threads running on multiple cores, because it takes a while. You can also do arbitrary precision fraction arithmetic, where you take fractions and multiply them or divide them or so on to get the results. And then there's also a way to take a so-called mixed fraction and, create a mixed fraction from a so-called improper fraction. So if we have 18/4, that's actually an improper fraction, which is kind of a funny name. Sounds like it did something wrong. You should get a citation or something. And we can convert it into a mixed fraction like 4 1/2. And you can get the code for this in a lot of the examples we're about to talk about. OK, so let's talk about the case studies really quickly, and then we'll jump into it. We're using these case studies in order to demonstrate how to do various operations on big fractions. And of course, that's just an excuse to show off all the cool features in Project Reactor, dealing with synchronous programming, which is the exception, that you would not go to the trouble of learning something as convoluted as Project Reactor and reactive programming to do synchronous programming, because you can do that other ways much more simply. So we're really going to use it for asynchrony and concurrent programming and parallel programming and so on. And we're going to see a couple different things. We're going to take a look at a bunch of case studies that show how to do things with monos. And we're going to look at a whole slew of mono methods. I won't walk through them right now because we'll cover them in more detail. But remember, mono is something that can do an operation on a single value and then return the result that can be operated further asynchronously or not by other operators. So they're very much like, mono operators are very much like completion stage methods in Java's completable future framework. We're also going to talk about some Flux case studies that are going to show how to use fluxes. And as usual, as is the model with Flux, there's usually a set or a group or a list of something that we're working on. So we need to convert that list or whatever into a flux, which then allows us to do streams programming on it using asynchronous processing features, which are super cool. And we're going to look at both fluxes and parallel fluxes, which will do these things in a more concise way. And then we're also going to have some fun for a couple of the examples demonstrating how you can take the Java Streams framework and use it together with the Project Reactor framework. And what's kind of interesting about this, if you think about it, many people, not really myself, sadly, are able to speak and read and understand multiple languages, multiple natural languages. And I took French when I was in junior high school and high school, but as with most things, if you don't practice, you forget it all. So I can basically say my name in French. That's like, you can remember the things you learned like the first day of class, je m'appelle or something. But what I'm pretty good at over time is learning the different paradigms of programming and then converting between them and being able to take something that's written in parallel streams and then think about how you would do it in reactive streams or so on. That skill, which I've mastered and honed over decades of thinking about this stuff, of course, is exactly the kind of thing that a large language model can do very quickly too. And so you continually have to ask yourself the question, how do I differentiate myself from an AI model? And that's going to be a really interesting question as we move ahead. By the way, I've also discovered, I spent a lot of time lately playing with LLMs as I'm doing the examples and the programming stuff. And usually when it knows what it's doing, it's really, really good. And as you get better at prompt engineering, you can usually coax it to give you pretty much exactly what you want. But on the other hand, there are times when it's not giving you what you want, and you can waste an inordinate amount of time and effort trying to convince it to tell you what it wants. And usually what's just happened there is that it simply hasn't been trained on whatever it is you're asking it to do. And so it'll start guessing and making all kinds of speculative wrong results. And so often I find after a short period of time, if I'm not getting what I need to go elsewhere to learn about this. So learning how to interact with these somewhat noisy and faulty LLMs is going to be another key piece of what we do down the road, I believe, when we use this for software development.